So today's topic is understanding DFS and 6 gigahertz AFC. And if you haven't joined me before, my name's Jim Vada. I'm the Chief Wireless Officer here at Seven Signal. If I did the thing Don did, you'd see like 3 of me all at once. That would be pretty cool. Maybe next
It's really
time.
cool though. I like that effect.
Yeah. Good feedback on that in the chat. But today's topic is DFS and 5 gigahertz and AFC and 6 gigahertz. We're going to start with DFS and start with just laying a little foundation about what it is. DFS is dynamic frequency selection, and what it does is it allows Wi-Fi to operate in 5 gigahertz spectrum where there are existing incumbents. So an incumbent is someone or a user that's been granted access to the spectrum, and they get priority. They probably are licensed, and maybe they bought a license to use that spectrum from, in the United States, the FCC. And so they get priority. If they're using the spectrum, they're using the channel, then Wi-Fi devices can't use it. Some of those are, the most common one we talk about is weather radar, but you also have other users, particularly in the U.S. with military and other users as well. So we're not allowed to transmit on 5 gigahertz DFS channels if an incumbent is there. The incumbent always has priority. And this is a feature that's supported commonly among enterprise access points to take advantage of that spectrum. But it's very rare to see DFS and the channels DFS allows supported by consumer APs. And that's because there's additional testing and certification and R&D that goes into supporting that band, which would make consumer gear more expensive. And of course, the consumer market is really driven by price. So just to look at the spectrum allocation here in the US, there won't be a quiz on the slide, but what this is showing is all the RF spectrum and how it's allocated. So each little rectangle is a different type of allocation. And one of the things you can see is that in some frequency bands, there's multiple users, multiple allocations kind of stacked on top of each other, right? And the idea there is, we want to give this user access to the spectrum, but they're not using it everywhere. They're not using it all the time. And what can we match, alongside that user that can, gracefully use the spectrum as well and get more out of it, because there's only so much radio spectrum available for everyone. Now, as you can see, almost all of it is allocated. So when the FCC grants a new spectrum allocation like the 6 gigahertz band, there's already incumbents there that have to be accommodated. Just like when the FCC sells spectrum to the cellular industry for expanding the spectrum available for 5G. Well, they're taking it away from one user to give it to another. And so those are very, charged and politicized conversations that take place. But for our purposes, when we're talking about the DFS spectrum in 5 gigahertz, it's this tiny little slice of the overall spectrum in around 5 gigahertz, where, as you can see, there's already a lot of existing users there that Wi-Fi has to accommodate. And I mentioned the FCC. That's the regulator in charge of RF spectrum rules here in the U.S. But in other countries, other regulators make the rules there, and there's no, there's no requirement that everyone has the same rules. It's beneficial, of course, to the industry that rules are pretty similar. But particularly with DFS, there's a lot of variation. So here's a chart from Keith Parsons at WLAN Pros that he shared with us, and it shows all the channels in the 5 gigahertz band across the top. And then you can see what channels here are subject to DFS, and then also what the different rules are in the different domains going down. So important point here, if we look at the DFS channels, that's channel 52 all the way to 144. That's 2/3 of the band, of the 5 gigahertz band, is subject to DFS rules. So we really want to use DFS channels as much as we can, because 2/3 of our capacity is locked up in these channels. And so understanding DFS and using it appropriately, it, can really benefit most high density networks where we want as many channels available to us as we can get. But you'll also notice that FCC and ISED and ACMA and ETSI, and I think there's a few little notes about Ofcom in here as well. They all have different rules, and these things change. Ofcom, I believe it was just last year, opened up the Uni 3 band to access for unlicensed users like Wi-Fi without a DFS requirement, like most of the rest of the regulators here do. So that's a look at that. What's the importance? Why do we, why is it so critical that we're using DFS and protecting incumbents, other than, they were here first, and so they get priority access? Some of these are pretty sensitive technologies in the DFS band where Wi-Fi is operating. It could be military users, satellite, radar, and more. One of the most common ones, though, that's and probably best understood, is terminal Doppler weather radar, and those use channels 120 through 128. These are ground-based weather radars with a pretty limited range, and they're installed near commercial airports. And their purpose is to detect very localized wind shear, because what the effect wind shear has on airplanes can be pretty serious. So this is what, like I was mentioning, this can be an effect of wind shear on an airplane. This is not a good thing to happen to a commercial airliner. So it's really important that we're not interfering with those TDWR services at local airports. And we'll talk about, the consequences that can arise from that. A couple of amendments to the 802.11 standard that make DFS possible. First, over 20 years ago, the 802.11d amendment gave us the ability to accommodate different regulatory domains and allow clients that are traveling between those domains to understand what domain they're in now, and what, how they need to adjust their transmit limitations. And then DFS in particular came to Wi-Fi from 802.11h. So sometimes you'll see that on a spec sheet, and that'll indicate, okay, this is probably an AP that supports the DFS channels. I would also, though, say, even if you see that, you want to clarify exactly which channels are supported and which aren't, because sometimes some channels within the DFS spectrum are still left out of APs that support it. So how do we use this? Most APs are sold with sort of a burned-in, hard-coded regulatory domain. Here's an example from a Cisco controller showing an AP in the A domain, which is within the US. And that's nice because essentially that means there's no nerd knob I can turn on that AP that'll, as long as it's got internal antennas, we'll say, that'll allow it to violate those FCC rules that are specific to unlicensed operation, but also how DFS is handled within the FCC. I just can't, cause any problems. If I had an external antenna that was super high gain, maybe I could start getting into trouble. But most of the time, we don't need to worry about making mistakes. Some APs, though, are sold with a configurable regulatory domain, in which case I could buy an AP like that and set it to Canada, for instance, where I might have a higher transmit power limitation in the 2.4 gigahertz band, and all of a sudden I'm getting better coverage with my AP. But now I'm in violation of violating federal law, and believe me, it's not it's not worth it. Also, that access point is sending a beacon that says it's in Canada to everyone within earshot to hear. So you're not being sneaky. You're advertising the incorrect regulatory domain, and it's easy to find. And clients, how a client responds to seeing an incorrect regulatory domain somewhere where its location services are telling them it's in the United States, probably could cause some issues too. So don't mess around with that. Let's talk about how the protocol works. There's a couple phases we go through. The first thing is the channel availability check, and that's something the access point has to do before it starts operating on the channel, and it involves a 60-second silent period most of the time. So once that AP goes to that channel, it's silent for 60 seconds because it's just listening. It's not transmitting it at all because that could mask any incumbent transmissions from it being able to receive them. So for 60 seconds, it's just listening. If it doesn't hear anything, then it starts operating on the channel. Now, in some cases, like those TDWR channels in the EU, that silent period is 10 minutes long. Because again, that's where those radar systems are protecting airports and airliners from wind shear. So they take that very, very seriously and say, no, 10 minutes of silence before you can operate here. So not a very friendly thing for clients if this is an active network to have an AP go completely silent for 60 seconds or 10 minutes. And the way this works is the AP is in charge. It does the monitoring and detection, and clients follow its lead. It's a master-slave relationship in the protocol, and clients can't operate on channels where APs aren't there and they're operating under their control. So while an AP is operating on that channel, it's continuously doing in-service monitoring, even after the channel availability check, listening for incumbents. And if it hears an incumbent, then the AP has to stop using the channel. So there's specific rules about that in terms of when it can come back, but actually what it actually must do, or what actions it takes is a little bit ambiguous. The important thing to the regulator is the AP and clients vacate the channel. That's the requirement from the regulators. And then it's up to the AP vendor to decide, okay, well, where are we going to go? When are we going to come back? Are we going to come back? And so on. So a couple things can happen. The AP can change channels immediately without any warning, and all its clients are just kind of left without an AP, and eventually, panic roam after having no communication from that AP. Or the AP can change channels gracefully using a channel switch announcement to let clients know what's about to happen. And then clients can decide, oh, okay, when this AP changes channels, I'll just go with it. And so, clients, again, that becomes a roaming decision, and clients are in charge of what they do in those circumstances. So often clients, when they hear a channel switch announcement, they don't want to play the game and go to the next channel and try to follow the AP. They just say, right, there's another AP over here. I'll just roam over there right now and avoid whatever might happen next. I think that's the most common behavior. So a quick look at some channel switch announcement frames. This is what you'd see in Wireshark if you captured these. And the channel switch announcement, it can come in a couple forms, either as a discrete action frame, which is what we see here, or it can be included in a beacon frame as an IE that just pops up routinely. A couple fields here to point out. The channel switch mode. In this case, well, actually, we'll go on and talk about them here on this slide. This is looking at a channel switch announcement in a beacon frame, just as a new information element that gets added when it's about to happen. So a couple interesting fields here. The channel switch mode. 0 means clients can continue to transmit with the AP during this brief period before it changes channel. And 1 means the client cannot transmit. It has to go silent too. So 0 is a little bit more client friendly. The count, channel switch count, is telling us how many beacons until the switch happens. So in this case, we're getting a big early warning. We've got 10 beacons before the channel switch happens, which is about 1 second long, which is a very long time in Wi-Fi. And then, of course, the new channel where the AP is going to go. So when it does switch, all the clients that want to follow it can go right to that next channel and associate there. There's another frame format called the extended channel switch announcement that can also be sent as an action frame or appended to a beacon. And the difference here is this adds the operating class, which tells the client a little bit more about where it's going to go, about what band it's going to be in, what range of channels it'll be in, and also the channel width. So we know in this case, it's going to the 5 gigahertz band and it'll be operating in 20 megahertz channel width. So right away, the client knows what channel width to expect when it goes there. So these are hex values. Wireshark doesn't natively decode these, but I went ahead and did the hex to decimal conversion here. And you can see we're going to channel 116, and we're going to go there in 2 beacons. So one of the things that you might note here is we're moving from one DFS channel to another. We're going to 116, which is another DFS channel. That's a little bit of a concern because that's moving to a new DFS channel means observing that 60-second silent period again. So this AP is telling clients, I'm going to this new channel in 2 beacons, about a quarter of a second. But also, I'm going to be silent for 60 seconds on that channel before I start operating. So you can see why in many cases, clients just say, forget it. I'm just roaming away from this and going somewhere where maybe there's a bit more stability. And kind of the final process, the final phase in the process is the non-occupancy period. So an access point that had a DFS event cannot return to that original channel for 30 minutes. And if it does go back, it still must observe that 60-second silent period. So the whole flow kind of looks like this. We've got the channel availability check. We go into an in-service monitoring mode. If there's an event, then we may transmit a channel switch announcement and go to a different channel. And then we have to observe the 30-minute non-occupancy period before we go back to the original channel, if so desired, which requires starting all over with the channel availability check. So the devil's in the details, right? Like I mentioned, the regulators just care about getting the Wi-Fi away from the incumbents that are potentially subject to interference. What the APs do after changing channels is not standardized, and the AP vendors have to decide rather for themselves. So you see different behavior for APs under the control of RRM versus being statically assigned channels. You see differences certainly between AP vendors, but also between AP models and code versions. And there's a couple things an AP might do. An AP, after a DFS event, might go to a non-DFS channel and just hang out there permanently. Might say, well, that was unpleasant. I'm going to stay on this non-DFS channel and until you come and statically assign me or restart DCA or something like that, I'm just going to hang out here on channel 36, for example. Or like we saw in that channel switch announcement, maybe it'll switch to another DFS channel. Maybe it sees that all the non-DFS channels are occupied and there are some available DFS channels, so I'll go to another DFS channel. In which case that would require that 60-second silent period. And then, after which we could see, and a lot of APs do this, instead of staying on the new channel it went to, after that non-occupancy period expires, let's go straight back to that DFS channel. And that can really actually kind of snowball into a kind of an ugly loop of switching back and forth between DFS and non-DFS channels. And, every 30 minutes changing channels, going silent for 60 minutes, DFS events reoccurring, and so forth. We actually see that, unfortunately, somewhat regularly. This is an AP channel chart from Sapphire, just tracking the channels that this AP happens to be using. And you can see in this, period, it's changing channels all the time between 56, 104, and 140. So those are all DFS channels. It's probably really trying to use channel 56. But it's probably going back there. There's a DFS event. Oh, okay, I got to switch. And then I want to, after 30 minutes, try to come back again and go there for a little while. Another DFS event. Unfortunately, the logic in channel changes can be quite disruptive, even if RRM is in charge of setting the channels that the APs are using. So something to keep an eye on. There is a little bit of hope. There's this project called the DFS Project. You can check it out on their website, but they're trying to describe the specific behavior for certain APs from certain vendors when DFS events occur. So you can kind of anticipate how your APs might react. Okay, so it's important to obey the rules. I mentioned that these are federal laws that are governing the DFS restrictions and requirements, and the FCC has teeth here. They have law enforcement capabilities here in the U.S. and they use them in particular to go after users, people that are interfering with terminal Doppler weather radar. And they've got this public web page where they talk about how serious this is and the fines and the people and naming and shaming and so forth of people that have been interfering with these systems. So again, if you're using DFS channels, which most everyone should try if they can to use them, obey the rules. Just an example too of what that looks like. One of the things they do is they will certainly fine and punish users. In this case, proposing $100,000 in fines. But also, in this particular notice, they made it clear that manufacturers have regulatory responsibility as well to make sure that their devices obey the rules and that users don't have the ability to switch DFS off or other kind of funny business like that. Hate to point this out, but there was a pretty significant field notice from Cisco maybe 18 months ago about a software issue that affected 8.5 and 8.10 code, where the DFS logic was broken, which could cause those APs to fail to comply with the DFS requirements. Pretty serious issue here. It affected the 2800 and 3800 platforms, among others. So go check that field notice out. It's 70577 if you're a Cisco customer, just to make sure that you're not affected by that. So DFS came with some problems. One is, uncertainty. We never really know if incumbents are there or not. A lot of these incumbents aren't ground-based radar systems. They're airplanes and helicopters and ships out to sea. And we can't predict when they'll show up and what channels they'll use and how often and what's the AP going to do. We also have this real problem with false positives where the DFS detection circuitry within a AP is just hypersensitive because it's important that the AP gets through an expensive and lengthy FCC certification for that so we can get out to market and start being sold quickly. And so we get a lot of false positives, unfortunately. Sometimes clients themselves get detected as radar. It's a real problem. And of course, we talked about the silent period and how that's an issue, but we also have an issue with slow AP discovery because clients aren't actively probing on DFS channels. They have to passively discover APs, which slows down AP discovery. And that's a challenge for VoIP. That's why some VoIP handset manufacturers discourage the use of DFS channels. And then, yes, the channel switch and silent period is quite disruptive. And with real-time applications and use on the Wi-Fi network, that's really going to be a problem. Okay, so one quick aside, I talked about a lot of the challenges and the incumbents we have to protect against. And a lot of people, though, assume, hey, I'm near an airport. So just that, because of that fact, I can't use the DFS channels. But all the major airports I visit, at least here in the US, they're all using the DFS channels. Here it is Atlanta International Airport, the busiest airport in the world. And all these DFS channels are in use. There's a couple that, at least from this particular vantage point, I don't see APs operating on. but they're even using channel 124 and 128. So just being near an airport isn't a reason not to use any DFS channels. In fact, if we use a very sensitive spectrum analyzer to see the impact of a terminal Doppler weather radar, this is the one local to me in Cincinnati, you can see that very thin red line is the only place where that weather radar is operating in this whole sweep of spectrum. So it might mean there's one channel I can't use, but it shouldn't just, take everything out of the mix. So a couple design considerations. Yeah, use the APs approved by the local agency for use, of course. Understand and comply with the rules set by that agency. Test the DFS channels you wish to use. So if you're lucky and this is a greenfield install, one of the things you can do is statically assign a number of APs to different DFS channels and just let them kind of bake in, see if you have DFS events. And if so, what channels are they most common on? Maybe just selectively remove those channels with high numbers of DFS events from your channel plan, but try to use as much of it as you can. If you have the ability, try to understand how DFS events will be handled by your APs. And certainly, if VoIP is mission critical, understand how AP discovery is going to be different and maybe take advantage of 802.11k to speed that up. It's less common today, but some clients don't support any DFS channels. Some support a subset, channels 120 through 128. Occasionally aren't supported, and channel 144 is more often the one that's not supported. So think about that when you're channel planning. So let's talk about what we're doing in the 6 gigahertz band with AFC. So we're leaving all the DFS stuff behind, and we've got this brand new 1200 megahertz of unlicensed spectrum that the FCC has made available here in the US. Other regulators have made available some or all of it in other areas. But there are incumbents here too. So instead of reusing that DFS protocol, which came with all those problems and baggage, we're doing something new for mainstream Wi-Fi. We're doing something called automated frequency control, and it's not a totally new framework. We got this was proposed in 802.11af for the TV white space operation, and also this is very similar to what private 4G, 5G uses in CBRS with the SAS, the Spectrum Access System. But what's different here is now the APs are not doing any incumbent detection. Actually, they're getting and we know that's a problem with DFS, false positives, and so forth. We don't have that problem anymore. And the best part is most APs can use the spectrum without any AFC requirement at all. Those are what's on the market today for Wi-Fi 6E. Those are low power indoor APs. And like the name suggests, they can only be used indoors in that low power, considered low by the FCC, but 18 dBm isn't too bad. The APs that are subject to these AFC rules are called standard power APs, and they can use external antennas and operate at much higher power. And they can only use a subset of the band as well. You can see in the channel chart, they can use Uni 5 and Uni 7, but not Uni 6 or Uni 8. So the flow for AFC, the access point or the WLC reaches out to the AFC service out across the internet, and every day it has to request access to the spectrum. The AFC does a ULS lookup. It gets from the FCC's database all the local 6 gigahertz incumbents in the area, and then using that data, it creates a model of the RF environment, and from that model, it says, okay, here are the channels that unlicensed users can use without interfering with the incumbents. And then it sends that back down to the AP or WLC and says, here's your spectrum grant. You can use these channels. And then the AP says, okay, well, if these are the channels I can select from, this is the one I'm going to select from that list. So it kind of looks like this in terms of the topology out across the internet. So, and one thing I should add too is the AP has to be able to geolocate itself, like with GPS, for example. So you may have heard, what Aruba started with their self-locating APs and announced at Atmosphere. That's, helping to solve that problem of geolocation for the AP to report to the AFC system. Now there's multiple AFC services, and they're not synchronized the way they are in CBRS. And this is all, this is still in development. So it's not all rosy. There's a couple problems. One of the issues is clients. So there are different classes of clients now in the 6 gigahertz band. And the two most common in the enterprise are the indoor client and then the dual client. And the indoor client can connect to low power indoors APs. And right now, that's perfect. That's all we need. That's all we have. And then the dual client can actually connect to LPI or standard power APs. The problem is, though, most of the 6 gigahertz capable clients in the US, at least, are only certified as indoor clients. So when standard power APs come out, they won't be able to connect to them or use them without potentially being recertified as dual clients. And I'm not sure if client vendors are going to be interested in doing that. So that's an issue. I will say it may not be a completely settled issue. I think there's awareness that this is a problem at the FCC, and there may be changes to the rules to prevent this from really snowballing, because this could prevent the rollout of standard power APs for client serving use cases almost entirely until most clients are dual client certified. But there are a lot of big benefits here as we're wrapping up to AFC. I mean, the major benefit is actually the last one, which is we just don't even have to worry about it most of the time. If we're using LPI APs, it doesn't matter. We just set it aside. When we do get into standard power deployments, though, it's such a breath of fresh air to have certainty through the AFC system that these are the channels we can use, and we're going to use them, and there's not going to be any uncertainty about a B-52 flying overhead and disrupting our whole Wi-Fi infrastructure out of the blue, like we have at DFS. No more false positives, right? We're not doing, the APs or clients aren't doing any incumbent detection at all. They're just dependent on a reasonable spectrum grant from the AFC. And that means no silent periods or anything like that. So it's really a significant improvement over what we had before. And hopefully, that dual client, indoor client problem can be resolved and improved going forward. So with that, Don, I don't know if we have a few questions or if we're gonna transition.
Yeah, there's a couple in here. We've probably got time for one, and then we've got a little time for Eric here. And I know that a lot of folks have been using the chat, and folks are answering those questions. But there's one or two maybe in the Q&A panel that we might be able to get to. And I'll do this first one from Brian. And it says, could you speak, and you touched on it a little bit here, maybe there's a little bit more you can talk to, but could you speak to mobile AFC? This is how outdoor high power APs might use AFC when they're moving by, looking up an area in a database instead of a single location. Do you have more details on that?
No, actually, Brian, that's new to me. I haven't heard about mobile AFC. So in fact, if my recollection is correct, the early draft of the rules said that standard power APs had to be in a fixed location. So I'll go Googling after the webinar.
Maybe one more here from Fang, and then we'll get over to Eric. Any solutions to allow AP switches from one DFS channel to another DFS channel without the 60-second interruption?
Yes, Fang, that's a good question. Maybe you work for a certain Wi-Fi vendor, but I'm aware at least Cisco has a solution. I want to say they call it Smart DFS or something like that, where they use it's either the RF ASIC or the XOR radio, and they use that radio that's not serving clients to do the 60-second silent period on the channel that the AP wants to move to, while the in-service radio is still serving clients on the current channel. And once that silent period is expired, then the client serving radio switches immediately and starts transmitting immediately. So a pretty interesting solution to that problem.
Indeed it is. So why don't we hand the controls over to Mr. Camuli here, who has joined us. This is the place during our presentation where we have 7 minutes with 7 Signal with Eric Camuli, and he walks us through, when he can, some of the products that are relevant to today's discussion. Eric, what do you have for us today?
Hey, really happy to be here. Thanks for having me, Don and Jim. Very excited. You should be able to see my screen. Let me know if you can.
We can.
Okay, awesome. So, hey, here we are, 7 minutes with 7 Signal. This is where we take a little feature inside of 7 Signal. We unpack it in order to show you how it can have a huge value to you and your organization. So, guys, here we go. I'm in Mobileye right now. We've been talking about DFS channels all day. I'm looking at a customer here. And as you can see, and actually in speaking with them, they're afraid to use the DFS channels. They're using these channels in Uni 1, and actually they're using a channel over here in Uni 3, and they do everything they can to avoid what's going on in the middle here. And it actually does cause them some problems. And so they just, they kind of indicate, hey, we've been told don't use them. It's too risky. It's too dangerous. And this is mission critical Wi-Fi, so we're not going to do it. And I would say, you know what? Use 7 Signal to look around the spectrum, because we got other folks that are using them just fine. And all I'm saying is that if other folks seem to be using them just fine, kind of like what Jim showed us with the Atlanta airport, then what I'm saying is that it may be worth investigating, researching, and trying, because boy, it could make a huge difference. Just a couple extra channels can make a huge difference in trying to provide better service to alleviate that contention, that congestion for all of the folks out there trying to use the Wi-Fi network. Let's look at our next screenshot right here. So here's an example, similar type of situation. It's also a hospital customer who did the research, who did the experimentation, and was able to determine, you know what, we can use these channels. And if we can, we will. And look at the difference. Boy, look at all of these channels. You've got the Uni 2A channels here. You've got these DFS channels in the middle here as well. You don't know until you try. And maybe you can't use certain ones like Jim was talking about earlier today. But again, maybe just, if you can use channel 64, if you could use channel 60, then go for it. do the experimentation. Those extra channels can really lead to a huge improvement in Wi-Fi productivity. I want to show you one more. I thought I saw that there was a question that came through, or maybe a comment that came through over the wire there with regards to, hey, isn't it true that home routers just completely avoid the DFS channels in order to just ignore this problem completely? And I think I found a good example of what you're talking about here. I think the answer might be yes. So this is one of our employees here. And as you can see, everybody in the apartment building is either on one side of the spectrum, the Uni 1 bonded 80 megahertz wide channel, of course, because when the ISP hands out routers, they're all on either channel 36 or channel 149, you know, and bonded to the nines, as you can see here. And when we went into this person's router to take a look around and see what was available, you guessed it, no other options. We were not able to use the DFS channels. They were just not even given to us as a choice. However, channel 165, it's the hidden gem. All right, be on the lookout for using channel 165, because as you can see right over here, we were able to set up shop on channel 165. And even though it's only a 20 megahertz wide channel, this person experiences much better performance as a result, as you can tell. So there you have it, guys. That's what we wanted to share with you today. Really interesting stuff. I think the lesson to be learned here is, hey, do some experimentation. If it's possible to eke out one or two channels out of DFS that your devices support and that aren't subject to maybe what's going on in the environment outside your building around you, then go for it. It's worth it. And so that's what I wanted to share with you guys today. And I'll just leave you with this. Remember, you and me, we can't see, we can't hear Wi-Fi, but 7 Signal can. Thanks for joining us today, everybody, and have a great one.
Thank you very much, Eric. We'll see you all next week when Lee Badman joins us. He's going to walk through Wi-Fi and network certifications that you should consider for your career. That's going to be a great event. And we're going to get a social media post up to wish Heather Dremel luck at the World Championship. So please show your support on that when we get that up on LinkedIn and Twitter later. Thanks for joining us, everybody. We'll see you all next week.